So this is a rampward incline question. We call that force problem type 3 in class. Type 2 is dealing with hanging signs. Type 1 was dealing with applied forces at an angle. So now with our incline, something very different happens with our coordinate system. Our coordinate system, I'll draw your attention to it, is rotated. It's tilted the same number of degrees as the ramp is. That makes the x-axis the plane of the ramp, or up and down the ramp, and the y-axis perpendicular to the ramp. That's going to lead to the force of gravity breaking up into two components. We've not had problems like that before. Usually force of gravity is straight along the y-axis. This time it is not along the y-axis. So it breaks up into two components that are along those axes. All right, let's do this problem. A 55 kilogram block sliding down an incline, coefficient of kinetic friction is 0.13. Incline makes an angle of 35 degrees with the ground. What applied force up the ramp is necessary so the block accelerates with a magnitude of 0.83 meters per second down the ramp? The net force relationship still applies. It always applies. So it's the sum of the forces in a particular direction. Now in this case, it's our x direction. So let's write down every single force that's there in the x direction along the plane of the ramp. We have the force of friction. We have the force of gravity along the x direction, and we have the force applied. So the applied force for this problem and the force of friction and that force, they're all along the x direction. So what we're trying to solve, I'll circle it in red, trying to solve for the applied force. In order to solve for the applied force, we need to know what the net force is, we need to know what the force of friction is, and we need to know what the force of gravity down the ramp is. So one at a time, I'm going to figure out what each of these values are and put them into this equation and solve for the applied force. So I'll do them in the order that they're there. I don't think it matters for this problem which order I do it. So the net force can be calculated through Newton's second law, knowing that force equals mass times acceleration. So the net force in the x-axis, or x direction, is its mass times the acceleration in the x, and we're given that in the problem. So mass, once again, is 55. Acceleration, 0.83. So those two numbers multiply to get 45.65. And that is newtons, and that's our net force down the ramp. Down the ramp is positive, the way I've labeled my axes, so I leave this as a positive value. Now I'm going to figure out the force of friction. Well, force of friction equals coefficient times the normal force. Now the normal force changes with the angle of the ramp, so I can't just go and write in mg here. I've got to first figure out what my y component of the force of gravity is. There's no additional forces up or down, it's just the normal force, which is equal in magnitude to the force of gravity in the y direction. So to figure out the force of friction, I need to figure out my FGY. So for this example, this is true. This isn't always true, but it's true for this particular problem. So FGY equals the magnitude of force of gravity times, in this case, it's going to be cosine of the angle, cosine 35. And I'll write that in next. Force of gravity is mass times, the magnitude is still mass times 9.81, so 55 times 9.81. But then, because there's an angle here, it's cosine 35. Good time to remind you that because we're on a ramp, the y component is now cosine, and the x component, when we need to find it, or if we need to find it, is our sine value. So 55 times 9.81 times cosine 35 comes out to be 442 newtons. Force of gravity in the y direction. That is, in magnitude, equal to our normal force, acting upwards. So I'm now set to calculate my force of friction. So force of friction equals the coefficient. The coefficient is 0.13. Normal force is 442. So force of friction, approximately 57 6.5 newtons. So I've got the net force along the plane of the ramp, I've got the force of friction, and now I just need my force of gravity, Fgx. That's going to be the magnitude of the force of gravity, sine of the angle. Again, it's sine now because we're on a ramp. If you look carefully at the geometry of the triangles, you'll see that the force of gravity is actually the opposite side of the angle. So force of gravity is our mass times 9.81, plus we're given it, and then sine 35. So Fgx is going to be 309.5 if you want extra decimal place there. Alright, so I'm going to take those values and put them back into my equation, taking into account which directions are happening here. So force of friction and the applied force are both negative. Fgx is positive, and my net force is positive because it's down the ramp. So net force is 45.65. That equals my force of friction, going to be negative 57.5. Remember, it's negative because it's up the ramp. It's acting opposite direction of motion. The direction of motion is positive for this one. Fgx is positive, 309.5. All that's left is Fa, force applied. If everything works out, this should be a negative answer. So if we're careful here with our numbers, 45.65, add it to 57.5, subtract 309.5, and we get, mistake here, 65 plus 57.5 minus 309.5 gives you negative 206 newtons. Would have to be our force applied in this example. Okay, so again, negative applied force just means we're pulling it up the ramp, which is the direction that we called negative.